My name is Pieter Kleer and I'm an assistant professor at Tilburg University in the Netherlands. So this talk is about congestion games, which is a very well-studied class of games, especially in the area of algorithmic game theory. So congestion games can be used, for example, to model traffic networks or scheduling problems, or more general other types of resource allocation problems that contain a certain strategic component. Now, in this talk, I will be focusing on a special class of congestion games, so-called load balancing games, that I will explain next. So, load balancing games consist of a number of objects. First of all, there is a set of players, which are A, B, C, D, F, G, H, and I in the example above. Secondly, there is a set of resources, which are the resources 1, 2, 3, and 4 in the example. Thirdly, there is a load-dependent cost function that is used to measure the amount of congestion on a particular resource. So in the example here, all the cost functions are so-called affine, in the sense that they depend linearly on the amount of congestion on a resource, but in general, we assume them to be non-negative and non-decreasing. And finally, there is a notion of a player cost under a given strategy profile. So the strategy profile is nothing more than a vector that assigns a resource to every player, namely the resource that they choose. And in order to compute the player cost, we can look at the cost incurred by a player on the chosen resource. So here, for example, player I chooses resource 2. There's 4 players using this resource that all place 1 unit of load on this resource, meaning that the total amount of congestion is 4 times 4 plus 2 is 18. And this is then the cost for player I. And the goal in a congestion game or in a load balancing game is for a player to choose a resource that minimizes her cost. Now, one way to play such a game is by means of better response dynamics. So in better response dynamics, the idea is that players can move around to another strategy in order to improve in order to improve their cost. So for example, here player I currently has a cost of 18, but if she would deviate to resource 1, she only has a cost of 4 times 3 is 12, so it's an improvement of 6. And here we use the strategy profile Si prime S minus I to denote the strategy profile in which player I unilaterally deviates to the resource Si prime, and all the other players keep their strategy that they had in the original profile S. Okay, so a bit more formal. Better response dynamics is the process where in every step one player is allowed to switch to a resource that may improve her cost. And it is well known that this dynamics converges to a pure Nash equilibrium, which is a strategy profile in which no player has an incentive to unilaterally deviate to another resource. So the players have spread out in such a way that no player has an incentive to move elsewhere. Now, in order to show that such a load balancing game, or more general a congestion game, has a pure Nash equilibria, we can use a potential function argument, and in particular, we can use a potential function introduced by Rosenthal, which is given by the expression phi here. And here there's one piece of notation, which is that XRS is used to denote the load on resource R under strategy profile S. And this is essentially just the number of players that use a particular resource R in the strategy profile S. Now, what Rosenthal showed is that congestion games are so-called exact potential games, which means that this potential function precisely captures the difference in cost of a player that unilaterally deviates to another strategy. So if player I deviates to some strategy Si prime, then the difference in cost for player I is precisely the difference in potential function value in these two strategy profiles. So there's a small example given here for those interested, but the main implication that this has is that a pure Nash equilibrium always exists. So this is fairly standard in the area of congestion games, but I wanted to introduce this Rosenthal potential already to you, because it will be used later on in the talk as well. So it will play an important role later on. Okay, now congestion games have been studied extensively in the last 20 years in the area of algorithmic game theory, and two of the most central questions that have been studied intensively are: is there, first of all, is there natural dynamics that converge quickly to a pure Nash equilibrium? So you might think of like better response dynamics or best response dynamics. And secondly, if such dynamics cannot be found, can we maybe compute a pure Nash equilibrium efficiently by other means? Now, it should be noted already that in general, the answer to this question is no, because it has been shown that computing a pure Nash equilibrium is a difficult problem in the context of local search problems. Nevertheless, there are many special cases known to which more positive answers to these questions exist. So, one example is for these load balancing games, for which it is known that better response dynamics always converge to a pure Nash equilibrium in a polynomial number of steps. So, here, polynomial in the number of players and the number of resources available to the players. Okay. Now, this was sort of the more classical setting regarding load balancing games and congestion games that has been studied in the last 20 years. Now, what we are interested in this work is a more dynamic equilibrium notion for these load balancing games or more general congestion games. So, the first part was referred to as the static setting, which referred to the fact that this pure Nash equilibrium is a somewhat static equilibrium concept in the sense that players play, for example, better response dynamics and they converge to a pure Nash equilibrium, after which the game basically ends. But in this work, we're interested in a more dynamic equilibrium concept where the equilibrium concept of interest is given as the stationary distribution of a Markov chain. So players never converge to a fixed strategy profile, but rather they converge to a probability distribution over strategy profiles. And we do this by studying the so-called logit dynamics. So these are a very well-known case of randomized dynamics that have been studied extensively in many areas, also many more applied areas. And the dynamics are fairly easy to describe. So given a strategy profile, what we do first is we select a player I uniformly at random. And after that, we let this player I deviate to one of the other resources according to a probability distribution, where the probability of deviating to a certain resource is given by this expression. Now, a couple of remarks here. First of all, this parameter B is something which is called a noise level, or the temperature of the system, which is not very important at the moment. But the more important observation to make here is the fact that this probability distribution assigns relatively more probability mass to resources that give a large decrease in cost. So the most probability mass is put on, or relatively speaking, most probability mass is put on strategies that give you a good improvement in cost. Now, it turns out that you can study these logit dynamics naturally as a so-called Markov chain. So I've repeated here the description of the logit dynamics. And you can naturally interpret them as a Markov chain, where the state space Markov chain, the state space of this Markov chain is given by the set of all strategy profiles. And there is also a transition matrix, which is induced by the procedure describing the logit dynamics. And one thing to observe is that there is a positive transition probability between two strategy profiles if and only if the two strategy profiles differ precisely by a player deviation. So one player deviating to another strategy. Now, it turns out that this Markov chain has a unique stationary distribution, which is called the Gibbs distribution, that is given by the expression below here. And the most important thing to observe here is the fact that the probability assigned to a certain strategy profile is to some extent proportional to the value that this strategy profile has in Rosenthal's potential. So this phi of S here is again this Rosenthal potential that I introduced earlier on. Now, some time ago already, people actually interpreted this as a game theoretical solution concept. So they said, okay, well, instead, or the way to look at this is that instead of looking at sort of a more static concept such as a pure Nash equilibrium, here you say, well, I'm defining my equilibrium concept as the stationary distribution of some Markov chain, of some dynamical system. And one of the nice features of it is that it's always unique, because a Markov chain if it has a stationary distribution, it always has a unique stationary distribution. Now, of course, the first algorithmic question that might come to mind is the fact, or is the question of whether or not these logit dynamics converge quickly to the Gibbs distribution. So whether or not they converge quickly to their stationary distribution. And unfortunately, it turns out that the answer is no in the setting of load balancing games, which can be illustrated by a very simple example, having 2 players and 2 resources. Furthermore, these 2 resources have a cost function that has the property that if one player uses it, then the cost is 0. But if 2 players use it, then the cost is m, where you should think of m as a large number. Now, in this case, there are 4 strategy profiles possible because we have 2 players and 2 resources. And there's 2 strategies where the players spread out over the 2 resources that approximately get a value of a half assigned to them in the Gibbs distribution. And the other profiles have a probability of approximately 0 in the Gibbs distribution. Now, the reason to see why it will take you a long time to converge to the Gibbs distribution is the fact that if you, for example, start the Markov chain in the top left strategy profile, then in order to go to the bottom right strategy profile, which also should appear as often as the top left one in the Gibbs distribution, we need to go through one of the other 2 strategy profiles where either A or B switches to the other resource first. But this happens with a very small probability, which is proportional to 1 over or e to the power minus m. So this also, roughly speaking, means that the number of steps you will need to get close to your stationary distribution is of the order e to the power m. So this is kind of a bad news situation. But on the other hand, this inspires us to or motivates us to look at 2 other questions, 2 more other algorithmic questions related to this Gibbs distribution. So the first one is sort of the question of does there maybe exist another Markov chain that converges quickly to the Gibbs distribution? Which means that the Markov chain, is there some Markov chain that is so-called rapidly mixing instead of slowly mixing? And secondly, if we cannot find such a Markov chain, can we maybe sample from the Gibbs distribution efficiently? Now, one way to look at these 2 questions is sort of as a dynamic analog to the questions I posed earlier for the computation of pure Nash equilibria in congestion games. So that's sort of also one way to look at this work, is that it sort of tries to analyze the sort of dynamic analogs of these more traditional questions that have been studied for the last 20 years regarding pure Nash equilibria. I should also say here that, but what do I mean by sampling? Well, sampling is meant in terms of approximate sampling, actually, which is the task of coming up with a randomized polynomial time algorithm that outputs every strategy profile to a probability distribution that is more or less the Gibbs distribution. And for those not really familiar with sampling, you can think of this as taking snapshots of your system at stationarity. So you have this Markov chain, you run it for a long time, and you somehow want to know, okay, if it might take a long time for this Markov chain to converge, but you nevertheless want to say something about what the equilibrium distribution looks like, then sampling is sort of the right problem to solve here. And it can also be used to answer, for example, a question such as, like, what is the expected congestion on a resource in this equilibrium distribution? These questions are also partially inspired by questions that have been studied mostly also in sort of the statistical mechanics and physics literature. In particular, there's sort of a close relation to the so-called Glauber dynamics for the Ising model, which also have a natural interpretation as sort of logic dynamics for so-called max cut games. I'll not elaborate on this slide anymore, but I added it here for completeness. So without further ado, let me mention the main result that we obtained in this paper. So it turns out that for load balancing games and for a slightly larger class of games, we are able to give a positive answer to this first question. So, like, is there some Markov chain converging quickly to the Gibbs distribution? And it turns out that there is a there's a Markov chain that is sort of a small variation on the logit dynamics that indeed converges quickly to the Gibbs distribution in load balancing games. And this result actually extends to so-called extension parallel congestion games. That's our generalization of load balancing games. Now, the dynamics, these dynamics proceed very similarly to the logit dynamics with a small twist. And that is that what we do is the following. So first we say with probability a half, we are allowed to interchange the strategies of two players. So we are allowed to sort of like interchange them or interchange the resources that they are currently on. And otherwise, with probability of half, we perform a step of the logit dynamics according to the definition that I gave before. And one should observe that this first step, so where we are allowed to interchange the position of two players, is precisely also what is needed to resolve this slow mixing in the example that I gave earlier on. So the problem was getting from the top left strategy profile to the bottom right strategy profile. And by introducing this move that allows us to interchange the strategies of two players, we can sort of resolve this issue. And it turns out that this is also sufficient to argue that the resulting Markov chain is rapidly mixing in load balancing games, and more general, these extension parallel congestion games. Now about the proof. So the proof mostly relies on a recent breakthrough result of Anari et al. Concerning the rapid mixing of the base exchange Markov chain under a strongly log-concave stationary distribution. So this is a Markov chain result that addresses the question of sampling a base of a matroid according to a so-called strongly log-concave probability distribution. And we use this result in combination with the result of Brandon and Yu that also, to a large extent, developed this theory of strongly log-concave stationary distributions. So to give you a very oversimplified idea behind the proof, what we do first is we relate these logit dynamics to a particular base exchange Markov chain for a relatively simple matroid structure. And then in order to apply the result of Anari et al., we need to show that the Gibbs distribution, which is the stationary distribution of the relaxed logit dynamics, satisfies this strong log concavity property. And it turns out that a sufficient condition for this is that Rosenthal's potential satisfies a property called M convexity. So this follows from a result of Brandon and Yu. And this M convexity is some kind of a discrete notion of convexity coming from the area of discrete convex analysis. And this property has actually been shown to hold for Rosenthal's potential in the case of extension parallel congestion games by Fujishige et al. And so again, these extension parallel congestion games were a slight generalization of load balancing games. So that's sort of just a brief idea of the proof, but sort of the main takeaway is that this Rosenthal function needs to satisfy this discrete notion of convexity in order to make everything work, in order to apply the results of Anari et al. So with this, I would like to conclude and leave you here with one slide that gives you an overview of the other results that we obtain in the paper. And I would like to thank you for watching this video.